This course is probability and statistics. You know that? Okay. So we'll have 15 weeks. 15 weeks, okay. Each week we will have 3-hour lessons, okay. 3-hour lessons each week. So I will divide it in 2 parts. The first 2 hours, I will introduce the theory, and then the third lesson, the third hour, I will let you do some exercise. We will discuss about that, okay? So we have 3 hours, 2 hours for theory, and then 1 hour for practice. Okay, and pre-quiz exercise is calculus 1, calculus 2, and linear algebra. Okay. Do you see? Can you see my screen?
Yes. Yes.
Okay. About the textbook of this course, we will use this book, Probability and Statistics for Engineers and Scientists. Okay. Do you have this textbook, or I need to upload it? Anyone who has this textbook already?
I think you should upload this for us to
I will upload it
for download.
Yeah, and then you can download it after. Okay. And we have a workbook for solving some problems. This the textbook, you can see it. Okay. Probability and Statistics for Engineers and Scientists, 9th edition. The authors are Walpole, Mayer. Okay. And the workbook is Problems in Probability and Statistics at my school. Okay. It's like this one. And I will upload all textbook and workbook for in this team. Okay. And you have a lot more references for our course. It can be in Vietnamese or it can be in English. For example, you can reference to the textbook Professor Tống Đình Quy. That's a famous one. Okay, you know that. The course of Probability and Statistics. You can read it in English. It's good too. And there are many others English, but I encourage you to use this textbook. I think that's enough for our course. But if you want, you can read a lot more. Okay. About the evaluation of the course, we will have 30% of the midterm. Okay, you know that already, and 70% of final exam. Okay, and sometimes I will check attendance to give you some bonus points. Okay, you know that. The maximum bonus can be 3 plus 3. or the minimum is -3. You know that already? Okay. So about the content of this course, we will cover 5 chapters. In fact, how many chapters? 5 chapters, okay? From chapter 1 to chapter 5. Okay. In chapter 1, we will introduce some basic notions of probability and some techniques to count. We can say counting techniques. Okay, that's the content of chapter 1. And then we'll see how we define what is the definition of probability of an event. Then we will introduce how to compute, how to calculate probability of an event by some rules like additive rules, multiplicative rules, and conditional probability. Okay. And the very important theorem in this chapter is Bayes' theorem and total probability. Okay. In this chapter. And then next, in chapter 2, we will cover what is the random variables and probability distribution of random variables. We will consider 2 types of random variables: discrete random variable and continuous random variables. Okay. And for probability distribution, we will introduce some popular laws of distribution like uniform distribution, binomial distribution, Poisson distribution. That's some types of discrete distribution. Okay. And then for continuous random variable, we consider exponential distribution. Normal and very important distribution law is normal distribution. Okay, chi-square distribution, student T distribution. Yeah. Next, in chapter 3, we will consider random vector, or we can say that's pairs of random variables. And we will introduce some some very important laws in probability theory. That is law of large numbers and central limit theorem. Yeah. Anyone who have heard about the law of large number or central limit theorem?
Yes, sir.
Yeah. Where did you heard about? Did you learn that?
I hear the lecture on YouTube.
Okay. Yeah. In English or in Vietnamese?
Both.
Okay, that's good. Yeah, there are 2 very famous theorems in probability theory. And next, in chapter 4, from chapter 4 to chapter 5, we will consider theory of statistics. Okay. In the first 3 chapters, we consider theory of probability, and then for the last 2 chapters, we consider theory of statistics. That means we consider sampling distribution, sampling theory, how to illustrate a sample from the population. And then we consider the two basic problems of statistics, that they are estimating problem and hypothesis testing problem. Okay. Yeah, that's our syllabus for the course. Any questions about this syllabus?
A small question on bonus point. How will you give bonus points to the student? Is it just based on attendance?
Yeah, sometimes I will check attendance, or sometimes I will give you a quiz, for example. Okay, like this one, you can see. I can give you a quiz like this. Let me. Let me show you an example of the quiz. Here we are. Yeah. It can be in form of multiple choice, or you need to fill in. For example, this one. Question 1 is multiple choice. Question 2, question 3, question 4. You need to give your answer. Okay. For example. Yeah. That's how I will grade you. Okay.
Okay.
Is it clear for you, Mr. Phạm Tiến Sơn?
In another class, other teachers they have a very specific. They are very specific about this. Some
Sorry, can you repeat
quite,
it?
I said that in
other
class,
teachers. What
yeah.
what other teachers do? What do they do?
So in class calculus 3, full attendance means +1,
yeah.
and then
Yeah, you have maximum +1 for your attendance check. Okay.
yeah, and
Yeah, if you attend all the I mean, you don't need to attend all, but if you don't miss any attendance check, for example, sometimes I will not check every time. Okay, but if you don't miss any attendance check, so you will have maximum 1 point. Okay.
okay,
And what
so,
else? What do you want?
And if I did all, if I do all the quizzes, it means +2, yeah, and then the total is +3.
Yeah. Quiz is like a homework. Okay.
Yeah.
I will check I mean the maximum for attendance is only 1. Okay, but the maximum for homework is 2. Okay. So quiz or homework, we have a lot of homework also. Yeah, for homework you can see this one.
Yeah.
And that means you can do your homework and then you submit it to me, and then I will check it and I will grade you based on your handwriting. Okay. Or you can type it.
Ah,
Whatever you have done. Okay.
yeah.
Is it clear for you?
Okay, it's clear now.
Okay.
Thank you.
Any further questions? Yeah, let's be positive. Let's be active. So I will be very happy if you ask me questions and you
Can you
each other.
upload both the workbook and textbook on
Yeah, of
the
course,
class
of course.
material now?
Yeah, of course I will do it. You want it now?
Yes, I want to
I think I
download
will
this.
upload it after this course because we don't need it now. Okay, I will
Yeah, maybe.
show
Yeah,
my
thank you.
slide. Yeah, I will base my lesson, my lecture on slideshow. Okay, so you should focus on my slides first. Do you agree?
Yeah, okay.
Okay.
Yeah.
So if you don't have any more questions, so let us start our lesson today. So the week one lesson is about some basic notions. You see, I will introduce some basic notions about probability theory. Okay, what are the basic notions of probability theory? We will see what is event and how to define a sample space. Okay, and then we consider the relationship between events. We consider the notion of union, intersection, mutually exclusive events, complement, exhaustive events, okay, collectively exhaustive events, and we consider some techniques to count. Okay. In fact, it's not easy to count, so we need some techniques to count it more effectively. Okay. We consider the rule of multiplication, permutation, combination. All of that, I think you have learned it from many other courses before. Okay. But now we will recover all the methods of counting. Okay. And then I will introduce the definition of probability. Let's start. Now we will consider how to define a sample space, how to use the notions, how to use the notation for sample space and events of sample space. Okay. About the definition of experiment, first we consider an experiment. So what is an experiment? So an experiment is the process by which an observation is obtained. That means for example, we consider an experiment, very popular experiment is, that is flip a coin. You know a coin? A coin has one head and one tail. So we want to see if it lands with head or with tail facing up. Okay. Or we walk to a bus stop, and the time you have to wait until the arrival of a bus, that is also an experiment. Okay. The third example is give a lecture, and how many? So we count how many students are seated in the fourth row. Okay, it's a random number. We don't know. So we consider the procedure, and we observe the procedure, and then we can measure it. Okay, so for our procedure, we consider flip a coin and let it land on a table. Okay, observe which side, head or tail. Facing up. Okay, and the result can be head or tail. We don't know before we conduct the experiment. Okay, yeah, that's the important point. We don't know before we conduct the experiment, so we observe it, and then we will see what happened after. Okay. So I think you can read it this after. Now let's consider the definition of sample space. The sample space of an experiment is the set of all possible outcomes for an experiment, and we denote it by S. Okay, what is the outcome of an experiment? An outcome is that way, or that is any possible observation we can see. Okay, we can observe. We can call each outcome a sample point also. So we consider S is like a space with many points. Okay, so each point is an outcome. Is it clear for you up to now? If you don't understand anything, so you can interrupt me and then we can discuss. Okay. Let's consider an example 1.4. Example 1.2. What is the example 1.2? We flip a coin and let it land on a table. Okay. So the sample space, now we can denote it by S equal the two possible outcomes. That is, they are H is head and T is tail. Okay. In the example 1.3, we flip a coin 3 times. So what is the sample space in this experiment? We denote it by S, and now can anyone who explain what does it mean H here?
It means if you choose 3 times, it's would be H or
H. What does it refer to?
It's OH.
I mean
outcome is OS.
Yeah, we get 3 heads. Okay. Yeah. I mean each time we get head. Okay.
Yeah.
So how many cases? I mean how many outcomes? Possible outcomes here. Anyone who can count it?
8.
8.
8
Why
is
why do
outcome.
we have 8 outcomes here? Can you explain it?
We have two kind of outcome, E, H, and T. Why we have 3 times to experience. So we will have 2 power 3.
Yeah, in fact, that's the technique of counting. We will consider that after, okay? Yeah, so you know already about that technique, okay? And there's a lot more example of sample space. For example, an experiment consists of flipping a coin. We flip a coin, and then we flip it a second time. If a head occurs, okay, that means the first time I flip a coin, and then I observe if it is head or it is tail facing up, okay, and if it is tail facing up, I stop my experiment. But if the head occurs, I will flip it the second time, okay, and I will stop it whatever the second time it is head or it is tail, okay. If a tail occurs, okay, I will do the other activity. If a tail occurs on the first flip, then a die is tossed once. You know, a die has 6 sides, okay, 6 sides. I mean, if the first time I flip a coin, it have the head happen, okay, the head happen. I will flip it second time. But if the tail happens, I will toss a dice, okay? I will toss a die with 6 sides, okay? So what is the sample space for this experiment? Who can tell us? Can tell? Okay. Anyone who can help us?
There are 3 possible outcomes.
3. Okay. Why do you say that there are only 3 possible outcomes?
If
Can you list on the outcome?
tail, head, and head tail.
Tail, head. I don't conduct the 3 times.
I think
I
this
conduct
example
the
in
experiment only 2 times. Okay.
I think it's a possible outcome.
Can you list it?
It is ST and T, but 1, 2, 3, 4, 5, 6.
Okay, that's right. The sample space is H. If the first time is head, then I flip the coin the second time, okay? And it can be H, it can be T, okay? That's the case when the first time we get H, we get head, okay? And if the first time we get tail, then we toss a die, so we can get the second time can be 1 dot on the side facing up, okay, or 2 dots or 6 dots, okay. So the sample space is this one. Okay. And the other way to illustrate the sample space using tree diagram. Okay, tree diagram. You can see here. The first outcome can be S or can be T. Okay. The second outcome depends on the first outcome. Okay. If the first outcome is H, then the second outcome can be H or T, and then we have a sample point HH or HT. Okay. If the first outcome is T, then the second outcome can be 1 to 6. Okay, and then the sample point is T1 to T6. Okay, is it clear for you now?
Yes.
Yeah, sometimes the tree diagram is very useful to calculate probability. Yeah, you can see that after. And now, sometimes we cannot list all the outcomes because there are many. Okay. Or sometimes the outcomes is infinity. So there are other ways to form the sample space. Is we can use the statement. Okay, statement or a rule method. For example, in this case, we use the formula like this. If we set all point x and y satisfy the condition x square plus y square less than or equal to 4. Okay. And now we consider the definition of an event in an experiment. An event, what is an event? An event is just a set of outcomes. Okay. That means it can be a subset of the sample space, or it can be the sample space itself. Okay. For example, we roll a 6-sided die and observe the number of dots on the side facing up. Now we label the outcomes E1 to E6. That means E1, for example, E1 is that denotes the outcome 1 dot. Okay. And now the sample space is E1 to E6. And now each subset of S is an event. That means we have event A. Event A is roll. We roll 4 or higher dots. Okay. For example, we have 4 or 5 or 6 dots. That's it. That is an event A. Or the number of dots is even. That is an event B. Okay. Or the number of dots is the square of an integer. So the outcome can be 1 or 4 dots. That is event C. Okay. Event C. Example 1.8. Wait for someone to make a phone call and observe the duration of the call in minutes. So now an outcome X is a non-negative real number. You know that? Okay. The phone call, the long of a phone call, it cannot be negative. Okay. It can be 0, but it cannot be negative. So the sample space is all the non-negative real number x greater or equal than 0. Okay. And how about the event A? Event A, we consider an event that the phone call lasts longer than 5 minutes. So that is A. We write it in this form, okay? So now we consider a simple event. A simple event is an event that consists of exactly one outcome, okay? So that means from E1 to E6 we have 6 simple events, okay? But for event A here, event A, event B, and event C, they are not simple event, okay? They are just called they are events, okay? And now we consider some notion on the relationship between events. Yes, it's the same thing as the theory of set theory, that they are union, intersection, complement, and other rules, okay? And how about the definition of union? Union of an event. Sorry, the union of events A and B is the event, okay? So the union of 2 events is also an event. That event, what is the property of that event? The new event, the union of the 2 events has the property that either A or B or both of them occurs, okay? Either A, one of them, or both of them occur, okay? We can use the Venn diagram to perform the union in this way, okay? And the intersection of 2 events, two events A and B, is the event that both of them occurs. Both of them occur, okay? We use the Venn diagram for the intersection like this. And the notation for the union is A cup B, or A upward, downward cup B, like this. Downward cup is for intersection and upward cup is for union, okay? And we can extend our definition to n events in this way, okay? And now we consider the notion of mutually exclusive. What is the notion of mutually exclusive? We say that 2 events A and B are mutually exclusive or disjoint events if one event occurs, then the other cannot, and vice versa. Okay, that means if A occurs, then B cannot occur, or if B occurs, then A cannot occur. Okay, and we can denote it by the formula A intersection with B equal to empty set, or that's an impossible event. Okay, we can say that's impossible event. That means A and B cannot occur at the same time or simultaneously. Okay, A and B cannot happen simultaneously. Okay, and we say that a collection of events A1 to AN is mutually exclusive if they are pairwise mutually exclusive. That means each pair of them is mutually exclusive, okay, for every pair of them. So we can use Venn diagram to show two disjoint events or two mutually exclusive events like this, okay. Let's consider an example of the two mutually exclusive events, A and B. For example, in the experiment toss a six-sided die, we can easily see that E1 event E1 to event E6, they are all mutually exclusive, okay? They cannot happen at the same time. Okay. How about the two events A and B in example 1.7? Do you remember the two events? A is the event that even number of dots have happened, okay? And B is the event that the number of dots is square of an integer, okay? No. Event A is the dots is higher than 4 or higher, and the event B is the dots is even number, okay? So A and B, are they mutually exclusive? Can you tell us? No or yes?
No.
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 Why?
No.
Why they're not mutually exclusive?
Because they have the same element.
Yeah, they have the one common outcome E4, okay, and two common outcomes E4 and E6, okay. That means they can happen at the same time. Yeah. And now for example, we can use the Venn diagram to show the mutually exclusive events. In this case, which of the two are mutually exclusive and which of the two are not? Who can tell us? First A and B, then A and C, and B and C. Which pair is mutually exclusive here?
Only B and C are
Yes.
mutually exclusive.
Okay, thank you. How about the union of A and B?
It's B.
A and B, A union B equal?
Beside.
Yeah, equal A, okay. And A intersects with B is B, okay. So they have some common outcomes, so they are not mutually exclusive, okay. And now we consider the notion of collectively exhaustive and complementary. A collection of events A from A to AN, A1 to AN is collectively exhaustive if and only if the union of them equal to the sample space. Okay, that means we get all the possible outcome of sample space if we take the union of A1 to AN. Okay, that means there's no other outcomes that is outside the union of A1 to AN. Yeah, it's not tip. That means we have no other outside. Okay, collectively, that means we use the union of them. Okay, so we have two parts here. The first part is collectively. Collectively, that means we take the union of them. Okay, exhaustive, that means we have no other choice, no other outcome outside the union. Okay, and that's easy to understand the definition of this one. Okay, how about the complementary event? The complement of event A. Event A, we have the event A here, and the complement is all the outcomes does not belong to A. Okay, all the outcomes that are not included in event A, and we can denote it by AC. C, that means complement, or A bar, like this one. You can use whatever you want. Okay. So here is the Venn diagram for the complement of an event. Okay. We have sample space S. We have in event A, and we have AC here. And now, can I ask you a question that what is the relationship between A and AC? Are they mutually exhaustive? Are they mutually exclusive, or are they collectively exhaustive? Have you heard my question clearly? You get my question? Let's consider the relationship between A and AC. Who can tell the relationship between them?
A and AC is both collectively exhaustive and and they are
Mutually
mutually exclusive too.
Mutually exclusive, that means they cannot happen at the same time.
At the same time, yeah.
Okay. They exclude each other. Okay. Yeah. So it's true that they are both mutually exclusive and collectively exhaustive. Okay. And now we can easily find the properties of relationship between union and intersection. Okay. For example, A intersect with empty set equal empty. Okay. The impossible event. A union with empty set equal A. That's easy. Okay. And the Morgan rules say that A intersect B take complement equal to the union of complement between the two. Okay, that's the Morgan rules. Have you learned about the Morgan rules in the property 8 and 9? Have you all heard about that?
Yes.
Yeah, that's very important properties here. If you take the complement of A union B, then we have the intersection of AC and BC. Okay, and if we take the complement of A intersection with B, then we have the union of AC and BC. Yeah. And now we consider event space. We have already learned about sample space, but now we consider event space. So what is event space? An event space is a collectively exhaustive, mutually exclusive set of events. That means they satisfy both conditions. The first one is collectively exhaustive. That means that we take the union, that then they are exhaustive, okay, and they are also mutually exclusive. That means there's no overlap between them, okay. There's no overlap between them. Here, the two conditions, 1.5 and 1.6 says that the first condition says that the union is sample space. That means they are collectively exhaustive, okay. And the second condition says that they are each pair of them are mutually exclusive, okay. That means there's no overlap between them, okay. Then after we can call that a partition of sample space. Let us consider an example 1.11. We flip four coins, okay. A penny, a nickel, a dime, and a quarter. We name the four coins: penny, nickel, dime, and quarter. We examine the coins in order, okay, in this order, and observe whether each coin shows a head or a tail facing up, okay. We flip four coins and observe if head or tail facing up, and now we will see what is the sample space and how many elements in the sample space. So we can easily see that the sample space consists of 16 four-letter words. We denote H is head and T is tail. So because we have four coins, so we have 4 to the power 2 to the power 4 possible outcomes. So there are 16 outcomes, okay. You can list it also. And now we consider the event AI. AI means outcomes with I, with the coin I facing head, okay. For example, A1, what does it mean, A1? A1 means we have one head only in 4 coins, okay? We have only one head. So we can list all the possible outcomes for this event. So we can see the first case is we have the first three coins, tail here, okay, and then the fourth coin is head, or we can have the head at the third coin, or the head at the second coin, or the head at the first coin, okay. So how many outcomes for this event A1? Many outcomes for this one? There are 4, okay, 4 outcomes. And then we consider the set B, including A0 to A4. That means A0, what does it mean, A0? The A0 refers to the event that there's no head occur in 4 coins, okay? And A1 will refer to 1 head, A2 refer to exactly 2 heads, A3 refers to 3 heads, and A4 refers to 4 heads. So they are all the possible cases. There's no other cases in our sample space. So we consider the set B now. Can you say that B is an event space? Who can clarify if B is an event space? Who can tell us? First, we consider if it is collectively exhaustive, and then we consider if it is mutually exclusive. Who can tell us? Guys, where are you? I cannot hear, I cannot see anyone who raised hands.
Between two event AI.
Yeah.
One they don't have any same element. Those.
There's no overlap between them. Okay. A0, that means that's exactly no head. Okay. A1, that means that's exactly one head. So they are mutually exclusive. Okay. Similarly for the other. Okay. Then each pair of them are mutually exclusive, right? A0, A1, A0, A2, each of them. Yeah, you can easily say that they are each pair of them is mutually exclusive. Okay, that's the first condition. And then the second condition is
because there's only five possibilities. Thus, there's one head.
We have only 4 coils, so all the possibilities of how many heads is 0 to 4.
0 to
the minimum number is 0, and the maximum number is 4. So we have no other possibility. Okay, no other possible outcomes. Okay. Yeah. So can we conclude that they are an event space? Yes or no?
Yes.
Yeah.
Event space.
That's a good example of an event space. Okay. How about if I consider the number of tail? Can I replace here? For example, A1 is the outcome with I tails. So can we conclude that they are also an the set B is also an event space? If I change from head to tail, do you get the same thing?
Yes.
Yeah, I think so. Yeah, so that means there's only one sample space, but there's a lot of event space. So event space is not unique, but sample space is unique in this case. Okay? You get it? Do you agree about that?
Yes.
Yeah. So let me recap it. We have only one sample space. In each in the fifth experiment, of course, in the other we have other sample space. But if we consider the specific experiment, so we have only one sample space, but we have a lot event space. Okay, it depends on how you define the event. Okay, and now we use some graphical illustration for event space. When we call that also a partition, you can see here. For example, we have sample space S here, and then we separate them into 4 parts. The first part is B1 and the fourth part is B4, and we call that partition of a sample space. Okay, partition. They are mutually exclusive and collectively exhaustive. Okay, and here, for example, yeah, that's a good way to show the event space. And now we consider an example 1.13. Now we consider the same experiment like in the example 1.10. We toss example 1.10. What is that example? What is that example? Yeah. In fact, that's example 1.11. Okay. So let A the set of outcomes with less than 3 heads. Less than 3 heads. That means we have 1 head, 2 heads, or 3 heads. Okay. And we list all the possible outcomes here for the set for the event A. Here in the first case we have no head, and the second case we have 1 head. The third case we have 2 heads. Here we have 2 heads here. Okay, less than 3 heads, so we mean there's no more than 2 heads. Okay, so we have how many outcomes here for the event A? We have how many? 6 here, 4 here, and 1 here. That means we have 11 outcomes for event A. Okay. And now we consider BI, the outcomes with I heads. Okay. And we already see that B0, the set B0 to B4 is an event space. So you can see that the event A now can be divided to 5 partitions. To 5 partitions here. You can see A equal to A intersect with B0 union with A intersect with B1. Okay, that means here you can see here. Here is the partition of sample space, but here is the partition of an event. Okay, partition of an event here. You can see here. If we move event A to the sample space here, so we have partition of event A. Okay, and now we can write it in this form. Okay, and I think we need to have some break between our class. Do you need some minutes to rest? Okay. We will have a break of 10 minutes. Is it okay for you?
Thank you.
So let's go back at 10:45. 10:45. Guys, let's go back to our lesson. Where are you? That nearly 100 guys, but I cannot see anyone. Ooh la la. Okay. So now we I will remind you of some techniques to count. Okay. Yeah, sometimes it's easy to count, but sometimes it's not easy. So we need some techniques to count it. Correct. Okay. Now the first rule is multiplication rule. This rule says if an operation can be performed in one way, and if for each of these ways a second operation can be performed in two ways, then the two operations can be performed in one multiplied by in two ways. Okay, that's the rule of multiplication, and this rule can be extended to n1, n2, and nk ways if we combine the k operations with different ways. Okay. For example, how many sample points are there in the sample space when a pair of dice is rolled once? Okay, that means we roll the two dice once at the same time. Okay. So the first die have 6 outcomes. Okay, and the second die has also six outcomes. So that means the pair of dice can have 6 multiplied by 6 or 36 outcomes. Okay, this is an easy example. And now we extend it in K different operations. Example 1.16. We shuffle the deck of 52 cards and choose 3 cards in order. How many outcomes are there? Do you remember the deck of cards? They have there are 52 cards in total. Okay, and now we choose 3 cards from the deck of 52 cards, and we put it in order. So we care about the order of 3 cards also. So now, how many outcomes are there? Or can you count? We have
52, multi 51, and multi 50.
You repeat it.
50, multi 51, multi 52.
Yeah, that's the correct answer. So we have 52 possible outcomes for the first card, and then we choose the first card. Okay, we have 52 possible outcomes, and now we choose the second card because there's only 51 left. So we have 51 possibilities. Okay, and then for the third card we have only 50 ways to choose. Okay, then the total number we employ the multiplication rule to get the answer. 52 multiplied by 51 and multiplied by 50. Okay, and now we consider the notion of permutation. What is the permutation? Permutation of n distinct objects taken k. Okay, that means we choose k objects from n objects and put it in the order. Okay, and how many ways to choose that? K permutation of n. We can say that k permutation of n. Okay, and we denote it by a k in the subscript. Okay, k and n here. And how many ways? For the first object we have n possibilities. Okay, and then for the second object we have n-1 possibilities, and so on. So the final number is n factorial over n minus k factorial. You can say that. Okay, so we note that the permutation of n objects taken k, we care about the order, but there's no repetition. Okay, no overlap. We choose each object only one time. Okay, only one time. For example, if we consider 3 lottery tickets, we draw 3 lottery tickets from a total of 50 tickets. Okay, we buy, for example, they have 50 lottery tickets, and we choose randomly 3 tickets. Then we distribute the 3 tickets to 3 employees in the order. Okay, how many ways to do that? And the total number possibility is k permutation of n of three permutation of 50. Okay, so it equal to 50 factorial over 47 factorial, and we have this number 117,600. Okay, and now the special case permutation is we take n permutation of n distinguished objects, and now we denote it by Pn or An over n. Okay, An over n, and we get the total number of n permutation is n factorial. So it's like we arrange the n items in order with no repetition. Okay, let's consider the example 1.18. A piece of equipment is composed of 5 parts. Okay, we consider an equipment that composed of 5 parts, and it can be assembled in any order. A test is to be conducted to determine the time necessary for each order of assembly. Okay, so if each order is to test once, how many tests must be conducted? That means we need to count how many tests we need to conduct. Okay, so the final answer is n permutation, and the number is 120. And now we consider the notion of combination. What is the combination, and how is it different from the permutation? Okay, now we choose k different objects from n different objects, and we don't care about the order of them. Okay, so how many ways to choose that? First, let's consider the order between them. So we have a k permutation of n. Okay, k permutation of n. So we have n factorial over n minus k factorial. Okay, but for each k object, we have already choose the permutation, the k permutation among them. So if we don't care about the order, so we need to divide by k factorial. Okay, so the relationship between combination and k permutation is the number of k permutation is a lot more than combination. Okay, and the k permutation p kn equal to k factorial multiplied by c kn. Okay, so we note that combination of n objects taken k has no repetition, but we don't care about the order. Okay, for example, a printed circuit board may be purchased from 5 suppliers. Okay, we purchase a circuit board from one of 5 suppliers. So in how many ways can 3 suppliers be chosen from 5? And the solution is we choose 3 suppliers from the 5 suppliers, and we don't care in this way. We don't care about the order of 3 suppliers. So the number of ways is combination of 3 from out of 5. Okay, we can say combination of 3 out of 5, or we can say C35, and the number is 10 ways. Okay, and now we consider sampling with replacement. If we have n different objects, so how many ways to choose with replacement an order sample of k objects? Okay, so we choose object 1 from n objects, we choose object 2 from n objects also, and then we choose kth object from n object. So how many ways to choose to do that? It's easily to calculate that. The number is n to the power of k. Okay, because the first object we have n possibilities, and the second object we have also n possibility, because we can choose with replacement. We can reuse the object. Okay, there's no constraint here, there's no restriction here. So each object of k objects, we can choose it from n objects. So in total we have n to the power of k objects. Okay, in this time we note that we care about the order, but we can repeat the object each time. Okay, for example, the access code to a house security system consists of 3 digits. So now we use 3 digits. For example, you need to put, for example, 425. That's the access code, and each digit can be any number from 0 to 9. So can you count how many different codes are available? Okay, how many? Can anyone answer this question?
1,000.
Why do you have 1,000?
Because each digit we have 10 number to choose.
Yeah, the first digit of the code can be chosen from 10 number 0 to 9. Okay, and the second digit?
And the second is also we can choose 10 number because it can be repeated.
Okay, and so on. So in total we have 10 to the power of 3, or we can say 10 cubed. So there are many ways. It's 1,000 codes, okay, available. So if you don't feel it is safe enough, so we can set up the 4 digits code, for example, and then how many codes are there if we set up the 4 digits code? Can you answer me? I mean, if we want more security, now we set up 4 digits code. So how many the codes are there now?
10,000.
Yeah, 10,000 and so on. If you want more security, you put more digits in your code. Okay. Yeah, that's the very popular code now. Okay. Now we move to the probability of an event. So you have already learned it from grade, I think from grade 11 and grade 12 at high school, I think. Okay. All of you have already learned about the classical definition of probability of an event, and now we will consider more definition, more ways to define the probability of an event. First, we consider also the classical definition. What is the classical definition of probability? The classical definition of probability says that the probability of an event. This is the general concept of an event, of the probability first, and then we consider classical. Now, we say that the probability of an event is a measure of our belief that the event will occur. That means the more likely the event happen, the bigger of the probability that is. Okay, so we list some axioms, or we can say properties of probability. First one is the probability need to be the number between 0 and 1. Okay. Some people say, why do you need the number from 0 to 1? The answer is we can define the probability more than 1, but if we want to make it the number is more reasonable, so we normalize it to the number from 0 to 1. Okay. Yeah. And probability of an empty set or the impossible event must be 0, and probability of the sample space must be 1. And the order of probability says that if event A is included in event B, so the probability of A must be less than or equal to probability of B. Okay, or you can say if A is the subset of B, then probability of A is less than or equal to probability of B. Okay, that's the general axioms, or you can say the general properties of probability. And now we consider some basic notions of probability. We say about the equally likely outcomes. Okay. For example, in the sample space S with n outcome E1 to En, we believe that each outcome is equally likely to others. That means there's no reason to say that one outcome is more likely than the other. Yeah, that's our assumption. Each one is equally likely. So now we can say that if an experiment with sample space S from event E1 to event En with each outcome is equally likely, then the probability of each event is equal to 1/n. Okay. For example, if we toss a coin twice or 2 times, so what is the probability of the event that at least one head occurs. So let us list the outcomes of the sample space here. So we have 4 outcomes. Okay, we toss the coin twice, so we have 4 outcomes. So if the coin is balanced or the coin is fair, we say the coin is fair. So then each outcome, head or tail, is equally likely to occur. Okay, that means probability of getting head or getting tail is equal to each other and equal to 1/2. Okay, in each coin. Okay, and now we have a probability of each event, simple event here, H8 or HT, we call that simple event. So probability of each event is equal to 1/4. And now we consider the event A with at least one head occur. So we list it as H8, HT, and TH. And now the probability of A equal to 3/4. Okay. And now we consider the notion of theoretical probability or classical probability, in fact. Okay. If an experiment can result in any one of n different equally likely outcomes, we consider this definition. The assumption should be all the n possibility are equally likely outcomes. Okay, and if we have exactly m outcomes for the event A, so the probability of A is equal to m/n. Okay, so that means we divide the probability of A equal to the fraction of, we divide the number of outcomes correspond to event A to the number of the total outcomes. Okay, total possibilities outcomes. Okay, for example, a statistic class for engineers consists of 25 industrial measure. Okay, 10 mechanical measure, 10 electrical measure, and 8 civil engineering students measure. Okay, we have 25, 10, and 8 students in each group. If a person is randomly selected by the instructor to answer a question, so we how to calculate the probability that a student is an industrial engineering major, and what is the probability that we can choose civil engineering or an electrical engineering major. So we denote, let us denote I, the event that we choose the student measuring in industrial. M, student is from mechanical, and E is from electrical, and C is from civil engineering. Okay, and now we can easily see that the number of outcomes in correspond to event E is 25. Okay, and the total number is, we combine all of the 4 different measures. Okay, here we have in total of 53 students. Okay, we have in total of 53,000 in this class, and in this case we have 25 industrial students. So the probability that we can choose a student from industrial majority is 25/53. Okay, and the second part of the question is, what is probability that we can choose a student from civil or from electrical engineering major? Okay, so we need to calculate the probability of C union E. Okay, C union E. So how many students from civil engineering? We have 8 students from civil engineering. And how many from electrical? We have 10. Okay, so in total we have 18 students from the 2 major. So the probability is 18/53. And now we consider the other way to define the probability. So the classical probability has some drawback point, because it assumes that every outcomes are equally likely. Okay, but in reality, sometimes the assumption does not hold. So we need another way to define a probability of an event. So this is the other way to define that, and we call that the empirical probability, or we can say that that is the statistical definition of probability. If an experiment is performed n times, and then we count the number of times that the event A occurs, we call that the relative frequency of A. What is the relative frequency of A? Relative frequency of A equal to the number of times the number A happens divided by the size of the sample space. Okay, so we define the relative frequency by this expression. Okay, and now if we conduct more and more experiment about the event A, or we can say if we let n tend to be infinity, or we conduct more and more experiment, then the law of large number, we will learn it later, say that the limit of the frequency of the relative frequency of equal, if the event A tends to the probability of A. So they define the probability of an event as the limit of the relative frequency of A. Okay, so for example, let's consider the very famous experiment about the coin. We flip the coin many times, so, and then we count the number of heads. So we divide the number of heads to the number of experiment we have already conducted. So we get the relative frequency f by divide m to n, and the statistician, in fact, the mathematician, Buffon, he's a French mathematician. He conducted 4,040 experiments. He flipped the coin 4,040 times, and then he got 2,048 heads. So the relative frequency is 0.5069. So the number here, you see, the relative frequency is very close to the theoretical probability of A. We know that the probability of getting head in each experiment is 0.5 or 1/2, okay? And then if we conduct the experiment many times, so we get the relative frequency is very close to that number, 0.5. And the other mathematicians already conducted a lot more experiment, and we get more and more exact the number 0.5 here, okay? So we will see the law of large number saying that the more you conduct the experiment, the more exact the relative frequency close to the theoretical number, okay? So we have the same properties for relative frequency. Relative frequency is also the number that lying between 0 and 1, and probability 0 refer to the event that A never occurs, and probability 1 if the event A always occurs, okay? And we note that the closer PA is to 1, the more likely it is A will occur, okay? I think we have enough theory today, and now we move a little bit to the practice. We will solve some of the problem here. I think now it's time for solving some problem, okay? And I will ask you to answer some easy questions. Can you see my screen on problem set? Can you see it?
Yes.
Yes.
Yeah. So now we need to do some problem on counting techniques. Okay. About the problem on experiments, I think you can do it at home. You can write it down by your handwriting. Okay. And the difficult one. Okay. And now we consider some problems on counting methods.
Can you send all the file?
Yeah, I will send it after. But now you can see in my screen. It's better now.
Yeah, okay.
But I will send it after. I will let you some minutes to finish problem 1.5 to problem 1.8. Okay. I think they are not difficult, so you can do it now. One finished, so raise your hand and so in your answer. Who can solve the first problem?
There are 32 different code words.
Yeah, can you, Liu Anh Đức, can you explain, can you clarify your answer?
What's problem?
Problem 1.5. Consider
can
final
you
code. Yeah.
1.5? Okay.
That means you have 5-digit code, okay? We can say that 5 bits or 5-digit code, okay? And each digit is 0 or 1, okay? For example, the code can be 0.
It's 2 power 5.
How many?
Exactly 3 zeros. So I think
first how many?
Firstly, you choose the 3 place for 3 zeros. It is.
No, I mean the first part of the question is how many different codes are there? At the first part, we don't need. We don't have any restriction. Okay. How many?
It is 2 power 5.
2 to the power of 5. So it is 32. Okay, 32 possibilities, 42 ways, 32 codes. Okay, and then how many codes have exactly 3 0?
It's 10.
Why? Can you clarify your answer?
It is 10 codes have exactly 3 0.
Why? Can you explain your answer?
Because it is exactly 3 0, so it is exactly 2 number 1 2. So I will choose the place for the 3 from 5, and it's 10.
Sorry, I cannot hear you. Your microphone has some trouble, no? Can you repeat it?
Yes. It is because have 3 zeros, so I am just choose 3 place for the 0.
I mean, as
so
the first step, you choose
from 5.
Sorry. As a first step, you mean you choose three place to put 3 0. Okay, 3 places to put your 0 first. Okay, how many ways to put 3 0?
It is 10 way.
The 3 of
10 ways.
5. Okay. You mean the combination C3 5? Okay. As the first step.
Yeah. And it's
C3 5. And then the next step.
It we and that's all. It is 10.
Are you sure that you finished your step, your process? Firstly, you should to choose 3 places to put the 3 0 digit. Okay, and then you need to choose the 2 rest number. Okay, we have 5 numbers. Do you think so? Lê Anh Đức?
I thought that's just 0 and 1.
Yeah.
So because it exactly 3 zeros, so we two place left is for number 1.
No other way. Yeah, you mean there's no other way to choose the two other digits? Okay, that means the two other is one,
Yes.
one already. Okay, yeah, that's a good answer. How about who else want to raise your hand? Who else? Nguyễn Hữu Tuấn Duy. Okay. You show your.
Yes, I'm here.
Mm-hmm.
The first question is, I think their answer is 64.
Yeah, 64. Not 32. Sorry.
Yeah.
Okay.
64 because because the 3-letter words, each letter we can choose A, B, C, or D.
Yeah. Mm-hmm.
And the second letter and the third letter is the same because we can repeat these words.
Mm-hmm.
Is it true? Is it true?
The final answer is how many 4 letters? You can.
Is 64. 4 letter.
Yeah, 4 letter words. You mean the problem 1.6? You're talking about problem 1.6?
Yes.
Right?
Yes.
Mm-hmm. Okay. So that's. Yeah. First part is how many 3-letter words can you form?
Yes.
How many?
It's 64.
64. Why?
Because each letter we could choose. We have 4 ways to choose.
Mm-hmm. Yeah. Okay. And the second part, how many 4 letters?
The second part, I think we could choose.
Each letter appears only once.
Yeah, 24 ways.
That's the 4 permutation, okay?
Yeah.
You mean 4 permutation. And how many the final answer is?
24.
Yeah. Okay, thank you. And now Nguyễn Hữu Tuấn, Mr. Nguyễn Hữu Tuấn, can you talk?
And Nguyễn Tuấn Duy. Yes, I can talk.
Yeah. Nguyễn Tuấn Duy.
Yeah, I can talk.
Can you explain your answer for problem 1.7?
1.7. Where I haven't read it, and just hold on a minute.
Mm-hmm. I think the problems are not difficult.
Yeah, you could choose another student because I just began to do the exercise.
Yeah. Next time, if you can, you should write on your screen. If you have a handwriting on your screen, it is better if you can show your writing yourself. It's more clear.
Okay.
We follow up. Okay. Can you share your screen? Can you share your screen?
My screen. My screen has nothing.
You cannot write. You cannot use OneNote, for example.
This.
Okay. Can you say it?
I haven't already finished.
Yeah.
Could you call other person?
Okay. The one who wants to. And now I think I should send you the materials so you can see it. You can read it after the lesson. Okay. Now I will upload all the material. Wait for me a little. Yeah, I will put it on general channel. Okay. You can see it in general channel. Wait for me. First, I will upload the syllabus of course. Tell me if you can see it on general channel. I already upload the syllabus of our course. Can anyone see it now?
Yes, we could see it now.
Yeah. Can you download and open it to check if it is available? And then I will upload the textbook. Textbook. Bruno Vampor. Yes, it is on the way uploading. And then the problem set. Okay, have you seen the textbook? Have you seen the textbook already?
Yeah.
Yes.
Yeah, textbook and then problem set. And then the slide. For this chapter. Problem set. Slideshow. What else? What do you need more? I think you.
Midterm test or on intern test.
What do you mean? Sorry.
Can you send some midterm
You mean
test?
You mean a sample test for you?
Yeah.
You want a sample test?
Yeah.
Okay, I will upload it also. Sample test. Yeah, done. In fact, we have a lot of questions also, so I will send you some more questions so you can finish it at home. Each week we need to finish some problem set. Beside the textbook and the problem set of our school, I will give you some more. Yeah, just to practice. Okay. Any questions? Feel free to ask me if you have any wondering or you have some more questions.
Okay, it's done. Thank you.
Probability. Which one? Problem set. Which one? So for your homework, I think you should try your answer in detail, so you can show me next time, or you can send me by email. So I will grade all your submission. Okay. So try to do it at home, and then I will based on your submission to grade you, to give you some bonus points. Okay. So do you have any further questions today? For today, so far so good.
The homework is the problem set or the problem set given first.
Yeah, for the given first week 1, and you can do it more in the problem set also.
Yeah.
Each week I will give you some specific problem set, and also you can do it in the problem set on the material also. Okay, you can do what you want. I can accept everything you submit to me. Okay. You don't need to do every problem in the problem set, but you can choose what you have done and what you are interested in. Okay. And then next time I will correct some of your answers. Okay. or if you need to clarify some of the problems, I will do it in the practice hour. Okay. Any further questions? Is it enough for today? No more people want to say anything?
Yeah, it's enough. Yeah, it's enough.
So we want to stop now?
Yeah, if possible.
Okay. So I hope that next time we will be more relaxed. So the first course, the first lesson, it was a little bit stressful. Okay. So, but next time I hope that all of us will be more relaxed, more enjoyable. Okay. We will enjoy our lesson more. Okay. I really hope that.
Okay, thank you.
If you have any question or any worries, you can ask me, you can discuss with me. Feel free to do that. No worry. So I'm here to help you, and we are here to learn more. We are not here to make each other more stressful. Okay, we need to make each other more relaxed. Okay. I hope that. So don't be stressful after this lesson. So just enjoy some reading and try to do a little bit some problems I have given you. Okay. So see you next week. I think there's only one lesson per week. So see you next week, guys.
Okay, thank you. See you later.